Okay, you guys. So in this part of the lecture, the last part of the lecture, I want to focus on synthesis of anti-aldol products. And specifically forming one anti-aldol over the other. And so just a quick review. We're still focusing on enantioselective reactions, i.e. forming one enantiomer over the other. And we already talked about our syn products. So just a really quick review from our previous 3 lectures. If you have a syn enolate using Evans oxazolidinones, in the presence of an aldehyde or carbonyl electrophile, and I used a really simple electrophile, you will get, in this case, the syn product, but the wedged syn product, because it all depends on the substitution of your oxazolidinone, right? We understand that this reaction proceeds via a Zimmermann-Trexler transition state. And I drew out the transition state for you in part 2 of this lecture series. So just make sure you take a look at that. And of course, if I use the enantiomer oxazolidinone, which is the wedged version, in the presence of my carbonyl electrophile, you are again going to get the syn product. But in this case, my syn product is going to be dashed. Right? And again, it's dependent on the substituent. On your oxazolidinone, we also drew the Zimmermann-Trexler transition state to this. And I said, hey, make sure you know how to draw the Zimmermann-Trexler transition states. Make sure you understand how to draw the chair conformations because it's a 6-membered ring. Unravel it to form the 2D product. And we talked about needing a boron Lewis acid to form the enolate and amine Lewis acid. We talked about the substituents on the boron, the fact that Evans oxazolidinones favor the Z enolate already, so the boron substituents further assist in the formation of that Z enolate. So this makes a lot of sense, right? We're going through our Z enolate to provide us with our syn products. But now we want to talk about our anti-products, like I just mentioned. But in this case, what I want to discuss is the fact that our anti-products are coming from Evans oxazolidinones and Z enolates. Okay. So why are we getting anti-products if we're forming Z enolates? We learned in the first part of the lecture that, hey, Dr. Lucero, Z enolates only give us syn products. And Evans oxazolidinone Z enolates also give us syn products enantiomerically. So why is it now that Z enolates are giving us anti-products? And the reason I'm introducing this is because It's really clever what they did. It's still David Evans' work. And Jared Shaw as a postdoc in the group. If you don't know, Jared Shaw is currently at UC Davis. He was the chair of the department for a while. He stepped down to just focus on research, but he currently is a full professor at UC Davis, has a really large research group. There have been a few of our Sac State students that have joined his group after their undergraduate work at Sac State. Um, so he occasionally comes for seminars. So if you're thinking of going on to grad school, Jared Shaw at UC Davis is someone who focuses on methodology and total synthesis. And when he was a postdoc at Harvard, um, he developed this method of forming anti-aldols from Evans oxazolidinones. So this was all at Harvard. Okay. So I want to highlight his chemistry just because he is someone um, who's so close to Sac State and has taken undergrads and grad students from Sac State. Okay. Let me give you where you can find this work before I jump into it. There are two publications from him and David Evans. It's a JACS publication. They're both from 2002, volume 124, and they're really quick reads. I think both of them are communication papers. One is from Org-Led, also from 2002, volume 4. Really easy to read, but I'll go ahead and try to summarize their work in this part of the lecture. Okay, so how do they form antiproducts from Evans oxazolidinones, since Evans oxazolidinones favor the formation of the enolates? So that doesn't change, right? And what they did was they used a different Lewis acid. So no more boron Lewis acids. Instead, what they focused on is using magnesium Lewis acids. Specifically, let me highlight this. Magnesium bromide or magnesium dichloride. Okay. So let me first introduce the general reaction of what's occurring. They did a really beautiful job at also doing computational studies on this, so they could try to explain what's happening. So I'll use the following example. And what's so great about this paper is that, again, they use magnesium bromide or magnesium dichloride as their Lewis acid. They continue to use dipea or triethylamine as their base. They add their aldehyde in there as well. And then finally, they add TMS chloride. Now, to remind you, TMS chloride is a protecting group, right? We talked about it in part 3 of this lecture series, where I told you, hey, it's a silicon group with 3 methyl groups and chlorine, and it protects alcohols. Well, they said, listen, the minute you form your O minus, we are going to add TMS chloride all in the same pot of the reaction so that you can protect the alcohol, the beta hydroxy carbonyl compound that you use. You can protect it immediately. You don't have to form the beta hydroxy and then deprotonate again and protect the alcohol. So it's literally two reactions in one round bottom. So two reactions in one round bottom, which is pretty amazing, right? Because the whole goal of organic chemistry is to cut down the number of steps, cut down the number of reagents, purifications that you need. You want to save time and you want to avoid using as many toxic chemicals as you can. And you do that by removing purifications between reactions. And this is exactly what it did. It combined two steps into one. And so, of course, you get the following. I'm going to try to squeeze it in here. You get the following product in this case. And just like before, we'll talk about the transition state. We'll talk about what's happening because this is pretty counterintuitive. And so if you notice, you're forming the anti-aldol product. Okay. So that's the first thing that I want you to notice. I'll go ahead and draw out the example with the enantiomer of my oxazolidinone. Oh, excuse me, where the reaction conditions are exactly the same. You can use either one of the Lewis acids, dipea or triethylamine. And just like I mentioned, you get the anti-aldol product. You also get the protected oxygen. Let me highlight that for you again. Okay. But what I want you to notice is that, of course, I'm going to highlight in a different color. These are syn to each other. Please notice that the syn comes from the first substituent alpha to the carbonyl and the substituent on the oxazolidinone. So when I say syn, I'm talking about the syn between the first substituent and the substituent on the oxazolidinone. Okay. So your first inclination is to think that, hey, it's proceeding via the E-enolate because E-enolates give us antiproducts, but it's not. You're still forming the Z-enolate. And so let's talk about how we get the anti-aldol products from a Z-enolate. And two, why is my first substituent alpha to the carbonyl syn to my substituent on my oxazolidinone? Okay. Okay. So still forming Z-enolate. So let me go ahead and draw out the mechanism. And we already know how to add an acyl group onto our oxazolidinone, so I'll save us some time. Presence of magnesium. I'll use magnesium dichloride. You can use magnesium dibromide. Again, it's a Lewis acid. Now, the beauty of it is that the magnesium, and I'll try it up here. Let me move this a little bit so I can give myself some room. Is not only complexing to the carbonyl oxygen, but it starts complexing to the neighboring carbonyl oxygen, the oxygen that's on the oxazolidinone. This doesn't seem to happen when you use a boron Lewis acid, okay? You treat it with dipea or triethylamine, right? I'll use triethylamine so that I don't have to draw out the dipea. Just like before, you deprotonate at the alpha carbon and you form your Z-enolate. Nothing new. So let me go ahead and draw out that intermediate down here. Remember, again, both carbonyl oxygens are complexing to my magnesium. And so here's the thing. When you add your electrophile, your new carbonyl, okay, nothing has changed here. We still have our Z-enolate favored. The thing is your transition state is no longer a six-membered ring chair conformation. It is no longer known as the Zimmermann-Trexler transition state. Okay. And they did computational work. I want to say that this is in the Orglet paper, not the Jack's paper, but they did computational work. And what they found is that the chair conformation was actually higher in energy than the boat transition state conformation. And it was higher in energy by 2.5 kcals. And so what they rationalized is that the reaction is proceeding via a boat transition state and not the chair transition state. Okay. And if you remember in sophomore organic chemistry, we tell you, hey, the boat transition state is terrible. There's all these sterics, right? But in this case, it turns out that the chair conformation is a lot worse than the boat conformation. And so what's happening in this case? And what they notice is that the magnesium, Lewis acid, is coordinating to all three carbonyl oxygens. And so when I drew out the enolate, I showed you, hey, it's coordinating to the carbonyl of the oxazolidinone and the oxygen of the enolate. But it also coordinates to the electrophile carbonyl as well. So it's coordinating to three oxygens at a time, and it's forcing the formation of a boat transition state. So let's talk about that transition state. So again, make sure that you understand how to see things three-dimensionally. You can rotate, you can see things from the top and the side. because in this case, it is a boat transition state, so it might be a little bit more difficult for you to see. Please come see me if you need help. But what I'll try to do is I'll try to color code things just like I did before. So let me go ahead and draw out my intermediate that I just drew up here, but I'm going to color code it red. Okay. And I'm just redrawing it. That's all I'm doing. It looks exactly like what I just drew above. And then I'm going to go ahead and add my carbonyl compound, i.e. my electrophile. And now what we're going to do is we're going to draw them coming together. Okay. And I will, of course, do it three-dimensionally. And then, of course, unravel it so that you can see it two-dimensionally. Okay. Let me go ahead and draw this enolate again. Negatively charged. They're complexing to my magnesium. Okay. Now my aldehyde is approaching. And my aldehyde, I'll write it up here, or my carbonyl compound, whatever you have, can approach from the front or back. In this case, my benzyl group blocks the front. So my aldehyde has to approach from the back. Opposite to benzyl group on the oxazoladinone. Okay. So let me go ahead and draw that. Okay. So I'm drawing my aldehyde coming from the back. Now, before I move on, please notice that I drew my hydrogen on my aldehyde facing the right. Okay. And I did that only because I've got a methyl group on there. If I would have added my R group on this side, my R group and my methyl group would have been crowding each other and hitting each other. And so sterically, it doesn't make sense to put your R group on the right. Okay. So my hydrogen is on the right. Okay. My carbonyl oxygen also coordinates to my magnesium. And I'm hoping that you can start seeing the boat conformation. To remind you, this is the conformation that we kind of want to see. My boat conformation. It's still 6 atoms. And so you can see the carbonyl oxygen chelating to my magnesium, regenerating my double bond, and then, of course, attacking my carbonyl oxygen. Okay. I probably should have drawn my aldehyde further in, but this is no longer a chair conformation. Okay. What I'll do is I will try to keep it in boat conformation so that you can see what's happening. What I'll also do is remember, in order to avoid the Evans oxazolidinone taking up so much space, I actually labeled as an auxiliary an Evans auxiliary, so I'll continue to do that as well. So this is still my new product, but again, I'm drawing it in boat conformation, so bear with me. And I'll also color code this. So notice how everything is drawn in boat conformation. Hopefully you can see that. Okay. Now what I'm going to do is, remember, we have TMS chloride present. So the minute that it attacks the carbonyl, it also protects the oxygen that I just formed. So I'm just going to redraw it. Let me move this a little down and give myself some space. Continue to color code. And this is my final product. Okay. Again, no wedges, no dashes. This is all three-dimensional. So now let me go ahead and draw it two-dimensional. You can look at it from the left. You can look at it from the right. I like to look at it from the right because I always like my Evans oxazolidinone and my carbonyl on the left side. So just like before, I number 1, 2, and 3. I'll continue to color code. I can now go ahead and draw carbon 2. It goes down. There's carbon 2. Please notice that the methyl group is coming out and poking me in the eye. So my methyl group is wedged. I then go up. So my carbon 3 is up. Again, notice how the hydrogen and the methyl group are on the same face, which means that the hydrogen is also wedged. And my OTMS group is dashed. Let me draw that in blue. Followed by my R group. If I want to replace my chiral auxiliary or my Evans auxiliary with the actual Evans oxazolidinone, I can go ahead and do that. And you should, because you can see once I do replace it, my methyl group, the first substituent alpha to the carbonyl is syn to the Evans oxazoladenone substituent, but everything else is anti. Not surprisingly, when you have your enantiomer, Evans oxazoladenone, it proceeds through the same transition state. The only difference is that your new carbonyl compound is coming from the front as opposed to from the back, right? Because the benzyl group is blocking the backside. So now your boat conformation is formed from the front of the aldehyde coming to the enolate, okay? I'll have you guys do that yourselves. Please feel free to stop by if you have questions, but I'll have you do that on your own, okay? Now let me go ahead and highlight this methodology using a total synthesis and its applicability to a total synthesis. Okay, so the total synthesis that I want to show you, it's really short. It's by Ashib Goswami from the Indian Association for the Cultivation of Science in India. And it's the total synthesis of cytospolite Q. And it's shown cytotoxicity against human lungs adenocarcinoma. Let me draw you the structure of this molecule. It's not as overwhelming as the other examples that I've given you. Before I do that, let me give you the publication. This is an ACS publication. It's known as ACS Omega, and it's from 2018, volume 3. Okay. All the publications that I've provided you thus far are all available through Sac State. We have subscriptions to all these publications, so they're easily accessible to you. And let me go ahead and draw out the structure for you. Again, just like before, we're not going to focus on the construction of the entire molecule, just highlighting how Jared and David's methodology was used. It's me. And again, it's a really quick highlight. They specifically focused on this part of the molecule and use Evans anti-aldol chemistry. So just like I always do, let me number my carbons so I can introduce this. And their target structure is as follows. I'll number it on this target as well. Okay. So really simple molecule, only 4 carbons, and all from starting material that's available. Again, our retrosynthesis, the starting material is cinnamaldehyde, which is pretty cheap and accessible. We've got tons of it in our stockroom. So let's go ahead and start off. I'll call this part 1 because I know I keep dividing it into different steps. So just to keep track of everything. And you introduce your Evans oxazolidinone. And the Evans oxazolidinone is as follows. Which is what we typically have used, which is really nice. We already know how to make this. And of course, our cinnamaldehyde. And we get our anti-product. Don't forget that when we get our anti-product, our first substituent, alpha to the carbonyl is syn to the substituent on the oxazolidinone. But you can see our anti-product. Okay. You then remove the Evans oxazolidinone. And they use lithium hydroxide, water with hydrogen peroxide. Remember, this is from lecture number 1. And you form your carboxylic acid. They then do a Fischer esterification. To form their desired ester. Right? Fischer esterifications are typically taught in Chem 124. Not typically, they are taught in Chem 124. And if you took Chem 25 here, it's one of your labs for Chem 25. It's the microwave lab. And then finally, ozonolysis. And this is from your first semester organic chemistry, where ozonolysis actually cleaves alkenes. And we briefly talked about it cleaving alkenes or reviewed it a little bit when we talked about SAMP and RAMP because it cleaves the SAMP and RAMP carbon double bond to nitrogen. And when it cleaves it, it gives you in this case, 2 aldehydes. Right? And it all really depends on the substituents on your alkene. Okay. And this is our final product. Let me try to copy and paste our target structure so that you can see that it's actually our target. Now, the only difference is, of course, that our aldehyde, in this case, is on the right side. And in this case, down here, it's on the left side. So if you flip it over, I can have my aldehyde on the right side, or excuse me, the left side. And my ester on the right side. So all I did was flip this structure over. And I'm done. And so they were able to synthesize part of their molecule using Evans anti-Aldol chemistry. Again, it's really clever because they didn't start with the five-membered ring lactone. They synthesized the five-membered ring lactone that's present in the natural product. This is your five-membered ring lactone. After they constructed this anti-aldol product, which is pretty cool. Okay, so there's your example, your total synthesis example. This is in no way the only way you can form syn-aldols and anti-aldols enantioselective. And so in our next lecture, we will be discussing other methods of making syn and anti-aldols. But we're only going to briefly discuss the other methods. There's just way too many methods nowadays. I just wanted to introduce Evan's pioneering work and Jarrett Shaw's contribution because Jarrett is just so close and just a really great professor to go work for at UC Davis. Okay.